Okay, everyone. Now let's have a look at the log normal probability plotting. First, let's have a look at the problem or example. What is the example? We have a multiple stress failure data, and we want to see whether they follow log normal distribution. So the problem is a semiconductor module has been observed to fail due to metal ions migrating between conductor lines and eventually causing a short. Both temperature and voltage affect the time it takes for such failures to develop. It is decided to model the kinetics of failure by conducting a stress matrix experiment using 6 different combinations of temperature and voltage. You see, this is 85 degree and 12 volt, and 85 degree 16 volt, 105 12 watt, 105 16 watt. And then we have 125 degree and 125 degree 12 watt. So, but the normal use condition is 25 and 4 watt. Under each cell, in each stress condition, we're going to have 50 semiconductor modules. And now we're going to read out the failure time at 24 hours, 100 hours, and then until 1000 hours. So those are the data we have. This is readout time. This is for the first cell and how much failures at each readout time. And similarly, we do the non-zeros F, and then we do the cumulative distribution. Okay, this is a cumulative distribution. This is capital F. Now let's see what we have. Q sum. Okay. Now we know that for log normal distribution, we have z equals to log t minus 50 log 50 over sigma. Z equals to phi inverse f. And then this is a nonlinear equation. We just multiply, we put this phi inverse f over here, then we multiply sigma phi inverse f, then plus t50 equals to log t. So log t become our response variable. And phi inverse f becomes x, so y equals to ax plus b. So sigma becomes our slope. Log t50 becomes our intercept. So different stress condition will also give nearly parallel lines if plotted together, but with different intercept, because t50 is a median, is also called scale parameter. So how to estimate f? For exact observation censored out of a sample size n, exact failures are known, then we use FTI is I equals minus 0.3 divided by n. N is a total number of products you're testing at the beginning. And the I is the I's failure. Okay, you sort them. And for readout data, with readout times T1, T2, Tn, the FTI is total failures by this time divided by starting sample size. Okay, now let's look at this example. Obviously, we want to plot log t phi inverse f. So this is log t. We have a log t already, and phi inverse, this is y, y1. y1, oh, I see, because we have a lot of zeros. So that's why. So we only count the first non-zero. So that's f1, how many we have? 6. And f3, how many we have? This is 1, 2, 3, 4, 5, 6. f3, we have 1, 2, 3, 4, 5. f3, y3, you only have 5. So the length is different. We only, because when we do the cumulative, the first one is 0, right? So we couldn't do the calculation with that. So we just count the non-zero term. And if we got the f, this is our y. we have for six different cells, because the length is different, we just go from the non-zero term to the end, different y. And x already we get non-zero terms. So x will become phi inverse. So that the length will be the same, x1, y1, y2, x2, x5, 4, y5, 4, x6, 4, y6, 4. You see y is log t. So log t, we just take different lengths. And the x, they are calculated from the cumulative distribution. Now we plot them. Let's see whether they follow the straight line. Yes, approximately straight line, right? So this is x is phi inverse f, so inverse transformation of normal CDF. And y is the logarithm of failure time, You see, they are approximately the different stress give approximately parallel lines. But because of this real data, they are the last one, the black one, KV. KV is extremely, it's 125 degree, 85 watts. This is very extreme stress condition. So it's a little bit slightly different from all other lines. But they are approximately straight lines. And for each line, we can estimate the sigma and the log T50. So we get sigma and this is a shape parameter and also the scale parameter. Let's see. This is sigma is the shape parameter and T50 is the scale parameter. Let's go back. Now our breakpoint come to here. Now we have x, and so we add ones. You see, we add ones, x1, and we add a column of 1, so that we can get the intercept. Then we do the linear regression. This is a least square linear regression \. So we got the sigma 1. T50 is exponential because it's what we have here is log T50. So we take exponential, we got T50. Now we just print them. Let's just print them. We got all the output. Cell 1, cell 6, what is a T50, what is a sigma? Let's see whether that's right. So T50, so we put T50, so cell number and sigma I over here. Okay. Now we got this problem solved, and we also learned how to do the probability plotting, log-normal probability plotting under different stress conditions. For each stress conditions, they follow a straight line, so it's log-normally distributed because we take the log. We take the log t as our y, phi inverse f as our x. So this is through those demo, I believe you have learned how to do the probability plotting. So this through the two examples, Weibull probability plotting or log-normal probability plotting or normal probability plotting, the basic idea is you have an equation. You want to convert this equation into a linear lines, and then you plot the data in this way, and then you try to see whether they approximately follow the straight line. If they don't follow, then they are not this distribution. And the same linear rectification idea can be applied to different kinds of probability plotting. So I only give you the examples of normal probability plotting, Weibull probability plotting, log-normal probability plotting. But for other distributions, you can follow similar Weibull, similar rectification idea. Okay. So this is a end of demo 2, log-normal probability plotting.